of obstacles via smartphone active sound sensing for pedestrian safety. This is the essence of our study. First, we try to predict both the distance and the relative velocity of oncoming obstacles in front of smartphone user using active sound sensing. And we also propose a novel probing signal that facilitates both distance and velocity estimation, and using sweep signals as well as sine waves. And we also propose a novel neural network architecture that automatically changes its input or automatically weigh in on the features extracted from the sweep signals as well as sine waves to estimate the distance and the relative velocity of obstacles depending on the mobility of the obstacle. So now let's take a look at the background of this study. We know that pedestrians use smartphones while walking on the sidewalk. While this is a very common practice, this is also a very dangerous practice because these pedestrians can get distracted from their devices and can bump into various roadside obstacles. So, therefore, capturing attributes such as distance and the relative velocity of oncoming obstacles is an important task for pedestrian safety, and specifically, distance and relative velocity is essential to calculate the possible collision time. To this end, additional specialized sensors such as distance sensors and proximity sensors have been employed to estimate these distance and relative velocity attributes of oncoming obstacles. However, in this case, it is inconvenient for the user as well as some of these devices are expensive. Therefore, smartphone active sound sensing has also been studied in obstacle attribute prediction, and in this case, we use the smartphone of the user to emit some kind of probing signal, and we capture the reflected waves using the same device. The two major types of probing signals we use in this research area are sweep signals as well as sine waves. So a sweep signal or a chirp is a sinusoidal wave that increases its frequency within a very short period of time. So this is a short discrete pulse that we can emit from the speaker of the smartphone, and we know that sine waves are long continuous signals with a constant frequency. So applications of such a system would include pedestrian safety systems, automation of managing alert levels of smartphones, as well as assisting visually impaired people. However, the existing systems have two major problems. The first one is limited types of obstacles such systems can cope with, and the second one is limited types of attributes that such systems can estimate. Taking a closer look at these problems, most existing studies focus on either static or slow-moving obstacles, while the sidewalk contains high speed and high velocity, high risk obstacles such as bicycles and jogging people. And secondly, most studies focus only on either predicting the distance or the relative velocity. So just one attribute, while both these attributes are necessary to calculate a possible collision time. Therefore, we set the goal of our research to estimate the distance and the relative velocity of both static and mobile obstacles prior to a collision, and we named our system offsets. Herein, we made an assumption that there exists a module that detects an obstacle in front of the user with the possibility of collision, which is a well-studied aspect in the previous studies. So to further understand why both distance and relative velocity estimations of static and mobile obstacles have not been spontaneously done in a singular system, we have to recognize what kind of attributes can be predicted using what kinds of probing signals. So as you can see, sweep signals can be employed to estimate both distance and the relative velocity of oncoming obstacles, and sine waves have been employed to estimate the velocity of the obstacles. So as you can see, theoretically it is possible to estimate both distance and the relative velocity of oncoming obstacles using just sweep signals. However, the hardware limitations of the smartphones only allow to emit several sweeps per second without affecting the amplitude of the immediate sweeps, which limits the sensing range. And therefore, to increase the sensing rate of such methods, they have to employ external microphones or speakers, or to only focus on slow-moving or static targets. Secondly, time series analysis of sweep reflections only provide pulse measurement on the mobility and the velocity of mobile obstacles, so which is an inconvenience in this case. So, according to the above investigation, we can understand that we need two types of signals to achieve the following estimations. For mobility and velocity estimations, we need continuous sine wave segments, and for distance estimation, we need sweep signals. So in the next section, we will discuss how these above signals can be employed to estimate the above-mentioned attributes. So for mobility estimation, we can use continuous sine waves. So in this case, we use the smartphone of the user to emit a continuous sine wave, and you can see the FFT spectrogram of a sine wave recorded by a smartphone. And when an obstacle in front of the user moves relative to the smartphone, it creates a Doppler shift on the reflected sine wave. And here you can see two FFT spectrograms we calculated using reflected sine waves under two different scenarios. So in the first one, the user moved towards an obstacle, which was a person in this case, a mobile obstacle, who also walked towards the smartphone user. And here you can see the Doppler shifts created by the ground as well as the moving body parts of the user. And you can also observe the Doppler shifts created from the obstacle. However, when the user moved towards a wall, which is a static obstacle, we could not observe any characteristic Doppler shift. This is because the relative velocity of the static obstacles towards the user is equal to the velocity of the user himself. Therefore, the Doppler shifts created by the obstacle gets hidden behind the Doppler shifts created by the user as well as the ground. And here you can see that we can use these characteristic Doppler shifts to distinguish between static and mobile obstacles. So basically, we can use the FFT information to recognize the mobility of the obstacle. Next, we will take a look at how we can use Doppler shifts to estimate relative velocity. So in this case, similar to the above scenario, we emit a sine wave from the smartphone, and when an obstacle moves relative to the smartphone, it creates a Doppler shift, and the frequency offset of these created Doppler shifts are directly proportional to the relative velocity of the obstacle. So for example, you can see three different FFT spectrograms here, which we collected using a static user who was holding the smartphone, and we asked a person to move towards this person in three different walking speeds. So as you can see, when the walking speed of the obstacle increased, the offset of the Doppler shift created also increased. And therefore, we can use the relationship of the frequency offset and the relative velocity to estimate the relative velocity of the obstacle. However, as I mentioned earlier, static obstacles do not create characteristic Doppler shift. However, we can still observe the Doppler shifts created by the user's body as well as the ground. So, when a user moves towards a wall in three different walking speeds, we can still see the increment of the offset of the Doppler shifts according to the walking speed of the user. Therefore, we can use these Doppler shifts to estimate the relative velocity of static obstacles as well, because the velocity of the user is equal to the relative velocity of static obstacles towards the user. So to estimate the distance between the user and obstacles, we use sweep signals. Here you can see the FFT spectrogram of a sweep signal, which we recorded using the smartphone. And here we calculate the convolution between the emitted signal and the reflected signal. And as a result, we get impulse responses of the sweeps. And what convolution essentially does is that it removes the effect of the emitted signal from the reflected signal, and it enhances the reflections from the obstacle recorded on the impulse response. So, if a user collected impulse responses while moving towards an obstacle, and if we stack these impulse responses according to the time they were collected, what we can observe is that the reflections of the obstacle getting closer and closer to the user with time. So this feature can be employed to estimate the distance between the user and the obstacle, and our method can estimate obstacle attributes from as far as 5.4 meters. So as you can understand by the above examples, we need both sweep signals and sine waves to facilitate distance and relative velocity prediction. So designing a probing signal was a challenge. At first we came up with this probing signal. You can see the FFT spectrum here, and it contains a continuous sine wave, and we emit sweep signals periodically as shown here. And however, this method gave us two major problems. The first one is filter power division problem. So when we try to emit two different signal components at the same time, the power of the speaker gets divided between these signal components, reducing the amplitude of the emitted signal. The second problem is signal power leakage due to frequency hopping. So when we try to emit two discrete frequencies adjacently from commercially available speakers, it creates noises that jump into the audible range of the human beings, which is an inconvenience for our user. Therefore, we came up with this second design where we serially emit sine wave segments as well as sweeps and inverse sweeps. And here we do not have the speaker power division problem, as we only emit a single signal component from the speaker at a time. And as the signal is continuous in the frequency domain, it eliminates the signal power leakage problem as well. As you can see, there are no noises jumping into the audible range of human beings. So for future experiments, we use this particular signal design. So this is the overview of sense. First, we collect reflected acoustic data from the smartphone, and we segment this time series signal into sweeps and inverse sweeps as well as sine waves. And we use the sweeps and inverse sweeps to calculate impulse responses, and we use sine waves to calculate Doppler frequencies. And we feed them into a neural network which estimate the mobility, velocity, and the distance of the oncoming obstacles. Here I would like to present the features that we use in our method. We have two major features: Doppler frequency or DF features, impulse response or IR features. So you can see the FFT spectrum of our probing signal, and you can see a magnified image of a sine wave segment with a Doppler shift recorded on it. And if you want to estimate the attributes, distance and the relative velocity at time step t, we select a Doppler feature frame from the FFT spectrum as shown in the figure that includes the Doppler shifts. And furthermore, we extract impulse responses from the previous 5 sweep signals, and we stack them according to the times they were collected. And here you can see the reflections of the obstacle moving closer to the user's position with time. So by time series stacking of impulse responses, we try to capture further information regarding the relative velocity of the obstacles as well. So this is the proposed neural network architecture. Here we input the DF and IR features into Doppler extractor and IR extractor that contain convolutional layers for feature extraction. And next we concatenate the outputs of the Doppler and IR extractors, and we feed them into our mobility estimator that estimates the mobility of the oncoming obstacle. Furthermore, we use the intermediate representation of the mobility detector, and we concatenate that with the outputs of Doppler and IR extractors, and we input it back into the distance velocity estimator that jointly estimates the distance and the relative velocity of the obstacle. So the basic idea here is that by employing the information regarding the mobility of the obstacle, we allow the neural network to select the most appropriate method to estimate the distance and the relative velocity. So for example, Doppler shifts contained in the DF features contain more information regarding the velocity or the mobility of mobile obstacles compared to the static obstacles. So therefore, neural network might leverage on the DF features to estimate the relative velocity of mobile obstacles compared to that of the static obstacles. So during the training of our neural network, we minimize the loss function shown here. The mobility loss, distance loss, and velocity loss are the losses of our mobility, distance, and velocity estimations. And here we introduce an integration loss that uses the relationship between the distance and the relative velocity as a supplement for our predictions. So what we basically do is we use the estimations of distance and relative velocity at timestamp t to calculate the distance at timestamp t minus 1. And we calculate the difference between the ground truth at timestamp t minus 1 and the calculated distance, and we aggregate it as a loss to our loss function. So this way we can preserve the relationship between the distance and velocity of the predictions of sense. To evaluate our method, we collected data from 5 static obstacle classes and 3 mobile obstacle classes, where the user walked towards different obstacles while holding the smartphone, and we asked the user to move in a random manner, in random speeds, and we instructed mobile obstacles to do the same to get much sparse data set. And we collected the ground truth of the obstacles using a LiDAR module, and we use 70% of data as training instances and 30% to test the model. And we also prepared some comparative methods as well. ObSense is our proposed method. Without integration loss, does not use the integration loss factor I mentioned earlier. Without mobility detector, does not use the intermediate representation of mobility detector. Only IR and only Doppler are variations of sense method that only used impulse response and Doppler frequencies respectively. So here you can see the results of sense method, and the F measure of the mobility detector was 94%, and the distance estimation error was 20.6 centimeters, and the velocity estimation error was 0.19 meters per second, lowest among the comparative methods. And here you can see the predictions made by the ObSense method compared to the ground truth of the distance and velocity predictions of a single obstacle encounter. So as you can see, even though the relative velocity of the obstacle changed randomly, our neural network can still predict the distance and relative velocity pretty accurately. So here you can see the distance and velocity errors per obstacle type. And something interesting here is that the obstacles involving a person have somewhat higher errors compared to the other obstacles. So we believe that this is because the reflections from the body of a person are weak compared to the other obstacles. So in summary, we propose a method to estimate both distance and relative velocity of static and mobile obstacles using smartphone active sound sensing. And we proposed a novel probing signal to facilitate both acoustic ranging and velocity estimation. And we also proposed a novel neural network architecture that takes into consideration the mobility of oncoming obstacle to accurately estimate the distance and the relative velocity of it. And as a part of our future work, we would like to recognize these oncoming obstacles, the class of these oncoming obstacles using acoustic sensing methods. Thank you very much. And if you have any questions, feel free to ask.
Thank you. So, again, time for questions. If you want to have a question, go to the microphone a little. And take it in your hand because you have to put it close to the mouth thing. I think it's on, you just turn it off.
Yes. Ashwin Ashok from the Stadium. Nice work.
Thank you very much.
So, questions and they're linked to this or them together.
Closer.
Yeah. So, have you? You're using acoustic, right?
Yes.
And you showed that you from your results you told that errors with humans is much higher than other.
Yes.
Have you looked into what kind of textures were there on the different types of obstacles, and how did they impact the Doppler shift as well as the impulse response? For example, I could have a very weird looking car
Okay.
with a lot of grooves, which would completely change your signature as
Yes.
opposed to a nice metallic finish,
Yes.
as well as the matte finish versus the clean finish.
Yes.
Have you looked into that?
So, not exactly, but I can give you an answer for that, because I have also been conducting research on recognizing the obstacle classes, and for that we use the frequency response of the impulse responses from the reflected sweeps. So we analyzed, so as you can see, we only use a very short sweep signal, about, I would say, 3 kilohertz range sweep signal, and we analyzed what kind of frequencies that get absorbed well, and we try to recognize the obstacle class using the frequencies that got reflected very well and absorbed very well. And in this case, we could recognize 6 obstacle classes with 83% accuracy. And so, as you mentioned, the signature actually changes according to the type of the obstacle, but I think we can use it to recognize the obstacle without considering it as a hindrance.
Just about the human thing, isn't it quite obvious that it'd be the? I was not surprised by that fact because probably using speech for ultrasound and it probably penetrate more into your body.
Sorry.
The sound signals would probably penetrate more into
Yes.
your body and then into your tissues.
Yes.
So you would get less reflections. I was not
Exactly.
surprised. It's nice that you can address that here.
Exactly. Yeah. Thank you very much.
Thank you for this talk. And my question is about, I guess such type of application require low latency.
Mhm.
So how was the prediction time?
Okay. So in this current research, we use an offline method to recognize these obstacles, or rather predict the attributes of the obstacles. So when we deploy such a system, we should confirm that the latency does not interfere with the oncoming collision times, right? So we did a literature review regarding the inference time of several neural networks that run on mobile devices. So, for example, the inference time of mobile network running on Snapdragon GPU of a smartphone has about 50 milliseconds of inference time. So, from the neural network side, I think our method would have lesser inference time because our neural network is much simpler. And we also have to consider about calculation of FFT spectrogram. We have also mentioned that in the paper. And there are studies that have quantized the FFT calculation times of the smartphones.
Thank you.
Yeah, so if you need one more question, okay. Quick question, quick answer, because we are waiting for the team session.
So thanks, this is Ahmed Hamid from UNC Charlotte. Thanks for the work, great work for a paper. Okay. Now let's talk about the implementation. It seems you want to do this on the mobile phone.
Yes.
And I'm just imagining, we can take more discussion offline, imagining, is this going to be running in the background all the time? Is it going to drain your battery? Do you have to fire up the app when
Yes.
get the phone out of your pocket.
Yes.
Are you really doing an overkill here with a simple signal processing approach? Would be much simpler and would achieve an adequate accuracy.
So the battery consumption is always a concern when it comes to acoustic sensing. So a simple solution for this would be recognizing when the user is looking at the smartphone, and this can be simply done using acceleration sensors and the gyroscope on the smartphone. So we just recognize when the user actually take out the smartphone and look at it while walking. And
So you have to run that process in the background as well, which would also consume your battery.
yes, using acceleration data, but acceleration data has much less sampling rate compared to acoustic sensing. So yes.
Or just when you start pedestrian navigation.
Yes.
When you click on that, you can also start that safety feature. Yeah. So, thanks again to the speaker. I think we will have much more discussion, but we have to go on.